Hello and welcome back to Calculus 3. The lecture is on the cross product, and this is going to be different now. It is still a way to multiply vectors, but it's very restrictive. Cross product is reserved only to certain dimensions. Only certain dimensions. So we have the 3D space is the space in which you can do cross product, and then the 7D and then 11D and so on. So only certain dimensions would have ability to perform this. So as in the previous lecture, we'll do the calculation first, and then we'll do the definition, and then properties, and then we're done. So the way to work the cross product, let's go first with notation. Notation is U cross V. So cross product is denoted by this. And now I'm going to actually use ABC. DEF as vector components. So what do we do here? Well, first, the way to compute this is to create as we compute the determinant of the matrix, we are going to place I, J, and K on the first line, and then the first vector goes first, so A, B, C, and then D, E, F. So that's the setup. For the matrix, make sure you have these vertical lines. Vertical lines like this means you have to compute the determinant of the matrix, and that's something that you might not know if you haven't taken linear algebra or you didn't see it somewhere in pre-calc before or whatever. So determinant of the matrix is computed this way. We start with I, and if you start with I, that will kill the row and a column. You are left with the 2 by 2 matrix B, C, E, F. Then we have minus J. This minus over here is usually a grade killer. So make sure you have the appropriate minus sign there. So we are done with I's. Now we're at J's. Eliminate the row and column. The matrix that it's left behind is A, C, D, F. And finally plus K. Eliminate row and column. You have A, B, and then D, E. So now, what we did is we created 3 2 by 2 matrices. So the signs that we are using are plus, minus, plus in front of I, J, K. As you can see over here, positive, negative, positive, to set this up. And then every time you put I, J, or K, you eliminate row and column, and then, right, for J, and the leftover are the positions that are not eliminated by eliminating row and column. Now, we are supposed to solve these guys. And the way to solve the 2 by 2 determinant is to multiply diagonal, BF, and you subtract the multiplication of the other diagonal. So I put this symbol in because it really helps. If you look at this way, you come in at the diagonal, there is a multiplication symbol in the middle over here. There's times, right? So B times F minus E times C. And then you're out. So B times F, here's a minus over here, it's flat, and there's your multiplication with a little x in the middle. So it's very simple to put this thing together. One more time, B times F minus E times C, and you're out. So now you follow that pattern for the other minus J, A times F minus D times C, plus K, A times E minus D times B. And that's that. So now I have to box all of this. No coughing.
No coughing? No cough.
And this is the way to compute the cross product between two three-dimensional vectors. So let me write that in blood over here. Cross product works in R3. It doesn't work in R2. So let's talk about, let's just do the cross product between two of these. So if I give you the vectors, let's say 1, 2, 3, very creative, right? Crossed with negative 2, 6, and 1.
Definitely will.
I, J, K, 1, 2, 3, negative 2, 6, and 1. We have I, and then the matrix is 2, 3, 6, and 1, minus J, 1, 3, negative 2, and 1, and positive K on 1, 2, negative 2, and 6. So 2 times 1 is 2 plus 18 is 20, so we have 20i. Then we have 2 plus 6 is 8, so negative 8j. And then finally 6 plus 4, 10 plus 10k. You can put this in a vector, 20, negative 8, 10.
Why do you add, like you get 20i? I thought it was like 2 times 1 minus 6 times 3.
So it should be like 18 minus 2 is 16.
2 minus 18 is negative 16. Right?
Yeah.
Yeah, negative 16, clearly. It's obviously negative 16.
J and K. Right.
I'm just testing you. Good. You all passed the cross product. Yes?
Shouldn't it be positive 7 and then positive 18 for the other parts?
We have 1 times 1 minus negative 2 times 3, and then all of that with a negative j in front, right? So it is negative 7. And then the last one, we have 6 plus 4 is 10.
I'm getting 18 for the last one.
Okay, let's take a look at the last one. If my pen starts working.
If your pen starts.
So the last one is 1 times 6 plus 4. 6 plus 4 is 10, right? Well, I guess this would be the wrap. Pen won't connect now. Come on. There we go. Yay. Now we know how to compute the cross product. It's time for the definition. So cross product definition, U cross V is U times V times sine theta. Which we can flip around. Theta is equal to inverse sine of U cross V, magnitude divided by magnitude of U, magnitude of V. Oh, there's a magnitude here as well. Oops. There we go. Angle between two vectors. And now we can put in R3 because we know this works in R3. So now we're going to have also the cool theorem, which says that if the cross product is 0, vectors are parallel. So if, no, let's go this way. So the vectors u and v are parallel if and only if u cross v is equal to the 0 vector. Now, when you have two vectors u and v, they define a parallelogram. So let's say these are your vectors u and v. So we have the parallelogram. And the area of that parallelogram is equal to u cross v magnitude. So u cross v is a vector. Cross product makes vectors. Very specific vectors, we'll see that, but right now we'll just say cross product produces another vector in R3. So the magnitude of that vector would be the area of the parallelogram that you get. So we have properties of the cross product. Cross product is not commutative, but it's very close to it. U cross V is equal to the negative V cross U. It's almost commutative. Associative property, good effort. AU cross BV is AB U cross V. And two distributive properties, U cross V plus W is U cross V plus U cross W. And U plus V cross W is U cross W plus v cross w. Again, any of these could be proven by simply assigning vectors u1, u2, u3 to u, v1, v2, v3 to v, and then just running through. Did that paper make all the way around? Okay. Everyone's good? All right, thank you. So to prove any of these properties, you will replace vector u with u1, u2, u3, and then you would plow through calculations. In a three-dimensional space, we have vectors I, j, and k. And we know that I cross j should give us vector k. They give you the full list of all combinations in a theorem, in a textbook. Hey, this stopped flickering. Nice.
Why does that flickering? What is flickering? What is flickering?
So the theorem over there shows all of the possibilities. You see that when you cross the vector by itself, obviously you're getting 0 because I is parallel to itself, which is I. But I cross j is k, k cross I is j, and j cross k is I. So from that exercise, we realize that, and this is extremely important, cross product gives us normal vector. So k cross I gives us j, and j cross k gives us vector I. Now, cross product gives normal vector. Behold your I and j. When you cross I with j, you get vector k. Observe that these two create the plane, which is your floor, and here's your z-axis, which is k. Now, I cross j is going to give you k. J cross I is negative k. It's not commutative, but it's almost commutative.
Yeah.
So, we have I cross j gives you k, j cross I, negative k. And we have that in properties of vectors, that if you swap which way you do the cross product, you get the vector. Why is it so? Well, remember, vectors, no matter which way you put the vectors together in space, they will always create a plane. That plane can only have a perpendicular vector up or down. And those are the two options, u cross v or v cross u. U cross v, vector n, v cross u, negative n. So any plane, this is now peeking into chapter 12 later on and so on. When you have a chapter, when you have a plane, the plane is described by its normal vector. That vector is the cross product of two vectors that define the plane. Pick any two vectors that define the plane. When you cross those two vectors, you will always get the same normal vector. And that's really cool. How many vectors do you have? You have infinitely many. No matter which two you pick, you will always get in a cross product the normal vector. It's really cool. So the cross product is producing normal vectors. The last part is to talk about application of this. Good. What we have is the torque. Torque is the force which acts in circles. Think of a screwdriver. You are applying torque in a circle, you are twisting the screw. The other is a wrench. If you have a bolt, you put a wrench and you push, right? The wrench is going to give you its torque again. You have something that's called a torque wrench. If you keep tightening the bolt and you're very strong, you snap the bolt actually, because of the way the forces work. So, especially in automotive, you have a torque wrench, and a torque wrench will say, this is how tight the bolts on brakes need to be. This is how tight the bolts for whatever component of the car need to be. You set that amount of torque, which is force, and then when you tighten, as soon as you reach that amount of torque, the wrench will start skipping and not allow you to tighten anymore. So the torque, so now we're talking about application. Is given by the lowercase tau, and it's a vector which is going to be radius crossed with a force, which is r times f magnitudes times the sine of angle in between them. So now, if you have a wrench, and there's a bolt in there, it almost looks like you're holding it with fingers. Yes. What do we have? The torque goes here. What I have between here and here is the radius. Well, maybe I should draw here. R. And over here, I have the force F. Breaker bars are very long because, well, you would know, since you're restoring cars. The breaker bar is very long because more of the radius, the longer the handle, more force you can apply, because the number over here that you're multiplying is bigger. We can do experiment here with the door. Here's another example. So that's the wall. Here's another wall. Now this is top view. This is where the hinge is, and this is the door. And this is where the handle is. So you are looking from the top. As you approach, you push with a force on the handle, and the door opens with the torque. Now, let's do the experiment here because we have the door. We apply force here because this is the furthest away from the side that has hinges. So, you push and it's easy, right? Because the maximum radius that I can have, right, times the force of the push. If you go here and you push here, you are not able to do. I mean, I am infinitely strong, but you guys will not be able to do it, right? So, short radius, right? And obviously, if you push on the hinge, the door will never open because radius is 0. You're multiplying by 0 in that absolute R situation. So that's why when we are opening the doors, we are always, right, as far as possible from the hinge. That's the torque, and the torque is this force that works in a circle, right? You have the force of push, which is straight, and you have this circular force which goes and turns things. So the wrench or the door hinge, and you can find obviously more of these things. In martial arts as well, right? A tall, skinny person, easy, not a problem, right? High center of mass, a lot of torque, just flies everywhere, right? You get a short, stubby person, tough to move. Low center of mass, not that much radius to work with, and that's why you will always find that those, some of those fighters, especially the heavyweight boxers and so, they're all like, look like little pile. And that's it. I hope you're not disappointed. That's the torque. Bye.